Hello everyone, welcome back to the NPTEL course on materials informatics. In this lecture we will be discussing about principles of statistical mechanics. Just as a recap of what we discussed in the last class, so we looked at molecular dynamics as a way to track trajectories and estimating kinetic or dynamic properties in systems, and we used diffusion as an example to look at the utility of molecular dynamics. And then there are several sort of things that we looked, several aspects of molecular dynamics that we looked at briefly in the past lectures. For example, choice of integrator is very important in molecular dynamics. So we looked at velocity Verlet as a robust starting choice. Choice of force field can really influence the accuracy of molecular dynamic simulations, and also how do you actually set temperature within a molecular dynamic simulations, and how do you use radial distribution functions for tracking structural changes within your simulation. So we looked at all of these aspects. So in this lecture there is a typo here. So in this lecture we will be looking at statistical mechanics and the ideas behind statistical mechanics and their use cases within the domain of material science and materials engineering. So in terms of schematics, I will be using schematics from a few different sources. So wherever I have used them, I will indicate the corresponding origins in the respective slides. Okay. So the first question is, why is statistical mechanics, right, and especially in a course related to materials informatics. So why do we have to bother about statistical mechanics? So if you look at ideas behind thermodynamics, right, that govern material behavior or material phenomena, thermodynamics as a theory itself is macroscopic in nature. So it is basically designed from a sort of a bulk viewpoint, where we do not take into account what happens to a given material at the atomistic or microscopic scale. So we take a material as a homogeneous bulk, right, and we define properties of that material. We estimate whether that material is in equilibrium or not, and so on, right. So that is basically the idea behind or the framework of thermodynamics. So if you want to incorporate microscopic inputs into this macroscopic theory, you need an additional tool, right. So and just to sort of indicate the importance of thermodynamics, right. So it dictates whether materials are in equilibrium or not, how stable a given phase of a material is, and so on, right. So in order to put in microscopic inputs into this macroscopic theory, we need another theoretical or mathematical framework, and that is where sort of statistical mechanics comes in. So it helps us connect microscopic models with macroscopic thermodynamic properties. So we devise models for describing how atoms or microscopic particles interact, and then how that sort of translates into larger scale thermodynamic properties. Briefly, the idea is that, let us say we have a system at hand, let us say 1 mole of ideal gas, something like that. So that is made up of many microscopic particles, so individual atoms that constitute this ideal gas. So you combine the interactions of these microscopic particles and then use statistical mechanics, right, as a mathematical framework. Then you basically get a description of how that system behaves in a macroscopic scale. So when you actually make experimentally relevant measurements. So basically statistical mechanics is a way to average or sum over individual particle properties to get the macroscopic values. So for example, if you sum over or average over individual particle velocities or individual particle speeds, you get an estimate of the macroscopic temperature, right. And if we find a way to average or sum over the number of collisions at an individual particle level, then we get an idea of the macroscopic pressure being exerted by the system. So statistical mechanics provides us a way to average or sum over these individual particle properties, and it acts as a link between theory and experiment. So if you think about properties of atoms, molecules, and so on, we have lots of theories mainly derived from quantum mechanics and so on to describe how they interact at a particular level, right. So how a bond is formed, what kind of energy do you need to break a bond, how much energy do you need to excite an electron, for example. So we sort of have very good theories for describing those particle or interparticular interactions. but experimentally we are going to do measurements at a very large scale, right. So it's a macroscopic measurement that we are going to make. So statistical mechanics can act as a nice link between microscopic theories and macroscopic measurements, right. And the other nice thing that statistical mechanics does is, we will also see it in the course of the next few lectures, is that it provides a new interpretation to entropy. So entropy in the case of macroscopic thermodynamics is just sort of defined as an abstract mathematical function, right. But the sort of influence or role of entropy in determining order or disorder in a given system, and the viewpoint of entropy being the distribution of what are referred to as microstates in a system, those all come from the lens of statistical mechanics. So without statistical mechanics we cannot add in new layers of physical interpretation to the mathematical function of entropy. And statistical mechanics also helps us answer a bunch of useful questions. So for example, if you want to understand why specific heat of a solid has a temperature dependence, right. So this has no answer from macroscopic thermodynamics, because in thermodynamics specific heat is again a mathematical function, right. So it can have a temperature dependence or not, but statistical mechanics tries to provide the reason why, right. So if it has a if specific heat has a temperature dependence, then why does it have so? Right. So that kind of answers we can get from statistical mechanics. So it's a fairly useful sort of theory to know, because it helps us find ways to predict properties of a material, especially in the bulk scale, which may be difficult to access entirely using just let us say density function theory based calculations or molecular dynamics simulations, or using sort of machine learning models, right. So even if you train very good machine learning models, you may need to use the principles of statistical mechanics to get very good macroscopic properties, right. And the other reason why we sort of cover statistical mechanics in this course is because it acts as the bedrock for most of the physics based models. So after statistical mechanics we will also be looking at some lattice models and sampling techniques, which can be used to get or predict phase diagrams of materials. So in order to do those, in order to use such physics based models, we need to actually understand the principles behind statistical mechanics. So so that is why it is a fairly useful theory to know and understand, so that we develop also expertise on the material side in addition to the sort of machine learning side. Okay. So before we get started on statistical mechanics, we just to give a brief refresher on macroscopic thermodynamics per se. So we'll have a refresher on thermodynamics and also a little bit of quantum mechanics, and then we'll get into the principles of statistical mechanics. So in terms of thermodynamics, there are three entities of interest. So the system that you are studying, that's basically your system, everything else is surroundings, and system plus surroundings is basically your universe, right. And there are four laws that sort of govern macroscopic thermodynamics. The zeroth law is basically the definition of thermal equilibrium. So if your system is in thermal equilibrium with its surroundings, then the temperature of your system should be identical to the temperature of your surroundings, right. And then we have the first law, which is basically the conservation of energy, restatement of the conservation of energy. We sort of define an overall internal energy of the system. So internal energy of an isolated system is constant, is the same, but for a non-isolated system, the change in internal energy of a given system should be equal to the net heat that is being transferred to the system and the net work done by the system, right. So del Q sort of stands for heat, and then W stands for work here. And conservation of energy is a fairly sort of even in classical mechanics, it is a fairly well known principle, but this is a useful way to restate, because we are including in, so work comes from classical mechanics, and sort of heat comes from thermodynamics per se. So it is a useful way to restate the principle of conservation of energy. And defining this conservation of energy also gives us what are referred to as state and path functions. So any system that we are considering can be defined as to exist in a given state, which is characterized by a bunch of state variables, right. So common examples of are temperature, pressure, volume, and so on. So these are all state variables. So so whichever variables dictate the state of a system, those are referred to as state functions. So internal energy of a system is a state function, but heat and work are basically path functions because they do not dictate the state of a system. They are only means of achieving a change in state of your system. So to go from, let's say, solid to liquid, but they do not define the solid or do not define the liquid. So energy conservation also gives rise to these state and path functions and a relationship between popular state and path functions. So it is a very useful entity to know. And then we have the second law. So second law has different statements. So it is widely considered as the sort of the negative law, right. So it basically states which processes are spontaneous, which processes are not non-spontaneous. It also goes into the definitions of reversible processes and irreversible processes. But if you want to take one sort of mathematical statement, right, you can very simply state second law, very simply state that the consequence of second law is that entropy always increases. The caveat is that entropy of the universe always increases, right. So that is basically the sort of one of the takeaway messages from the second law. And the way to mathematically quantify this is the change in entropy of a given system should always be greater than or equal to the heat transferred to the system and divided by the temperature of the reservoir or the surrounding which is doing this heat transfer, right. So for reversible processes this equality should hold, for irreversible processes you will have the inequality. So this is one way to mathematically state your second law. And then the third law of thermodynamics is also referred to as the Nernst postulate, because it was originally posted as a postulate and then later mathematically proven. So the Nernst postulate basically states that your entropy of a given system tends to go to 0 as the temperature of the system goes to 0 Kelvin. So this 0 is an absolute unit, so 0 Kelvin. So entropy goes to 0 as temperature of the system approaches 0 Kelvin. So that is the third law. So third law basically gives a very unique reference to entropy. So the other quantities such as internal energy, for example, do not have a unique reference. So you have to define an arbitrary 0 for any given system, but entropy of all systems, at least all ground state systems, are well defined. So they always go towards 0 as temperature tends to go to 0. So these are the main 4 laws on which thermodynamics is built on. And then just to sort of look at the other mathematical functions, right. So as I mentioned before, the consequence of conservation of energy is that internal energy of an isolated system is conserved, and we denote internal energy using this notation of E, right. So E can be written as this in this Euler form here. So it is Ts minus PV plus mu n plus xi yi. So T is temperature, S is entropy, P is pressure, V is volume, mu is chemical potential, and n is the number of particles having this chemical potential. So this is basically species dependent. In this case we are considering a single species to constitute our system, and then xi and yi basically correspond to any external work that can be exchanged by the system. So xi stands for some kind of intensive variable or field variable, think of electric field, magnetic field and so on, and yi is the corresponding displacement that the system can have. So for an electric field the system can have a polarization, for magnetic field it can have a magnetization and so on, right. So this is basically the Euler form of internal energy, and if we differentiate you actually get this this form here, which is basically you do not get the SDT form, you only get the TDS form, and this comes from how the conservation of energy is actually stated, right. So the change in internal energy of a system is defined as your TDS minus PdV plus mu dN plus xi dyi. TDS is you can consider this as the sort of thermal work or net heat that has been transferred to the system. This is sort of volumetric work, so expansion, compression. This is chemical work, right. So change in species of your system, and this is any other external work, right. So since an isolated system, if you have an isolated system and if that system remains at equilibrium, so if that system is actually in equilibrium, so we refer to equilibrium of a system as a time invariant state. So once a system reaches equilibrium, it does not again evolve with time, it remains in that state for the foreseeable foreseeable timeline, right. So if we define equilibrium as time invariant states in thermodynamics, so an isolated system is in equilibrium if your internal energy change of your system is 0. So in other words, if the internal energy of the system is not changing, then the system has hit equilibrium. Then the system has hit equilibrium and it is going to remain in that state forever, right. Although this statement only states that change in internal energy of the system is 0, we can actually show that your internal energy has to hit a minimum, right. So d of a system can be 0 if E is either minimum or maximum, right. So if your system is at equilibrium if E is at a minimum, so if internal energy is actually at a minimum. So we can actually show this, but for most systems, as long as we use this condition, it should be good enough to define what the equilibrium state of a system is. So isolated system is at equilibrium if the change in internal energy of the system is 0 or internal energy is at its minimum value. So continuing on with our thermodynamics, right, thermodynamics revision. So we can actually perform Legendre transforms of internal energy to give rise to other thermodynamic potentials. So Legendre transforms use this principle of equivalence between point and line geometries, right. So they are just different ways of representing the same mathematical function, but once you use the Legendre transform, you can actually change the boundary conditions, right, on your system. So the different thermodynamic potentials that you actually generate, they turn out to be the governing potentials at those corresponding boundary conditions. So basically they dictate whether your system is at equilibrium or not. So let us look at a few examples of Legendre transformed versions of your internal energy here. So if you take the case of enthalpy, so enthalpy is the Legendre transform of internal energy with respect to volume. So you can write it as H equals E plus PV here. And if you write the differential form of enthalpy, you basically get TdS plus VdP and plus mu dN. So the PdV term has gone off here. So you have TdS mu dN which comes from your dE term here, and then instead of minus PdV you get a plus VdP term here, right. So that's the differential form of your enthalpy. So enthalpy is also a governing potential for a given system under different boundary conditions. So enthalpy of your system does not change, or it basically hits a minimum for a system under equilibrium under adiabatic, isobaric and closed conditions. So if you take the case of internal energy goes to 0. So dE of system is 0, right. If your system is at equilibrium under adiabatic, isochoric under the same volume, and if it is closed, so if it is not exchanging any species. In the case of enthalpy, the isochoric condition is changed to isobaric. So under adiabatic, isobaric and closed conditions, if your system is under equilibrium, then the enthalpy of the system will hit a minimum value. So under these conditions, the internal energy of the system will not hit a minimum value, it will be the enthalpy of the system that hits a minimum value, right. So we can define other Legendre transforms as well. So we can define Helmholtz energy, which is Legendre transform of internal energy with respect to entropy, right. So the differential form is basically negative SdT here. So you have the TdS term being replaced by SdT, the PDV and mu dN terms remain. So under isothermal, isochoric and closed conditions, your system is under equilibrium if your dF of system is 0, or if your Helmholtz energy has hit its minimum value, right. So we can also define Gibbs energy. Gibbs energy is quite popular in the fields of material science and also chemistry and so on. So Gibbs energy is the sort of Legendre transform of internal energy with respect to both entropy and volume. So you can write it as E minus Ts plus PV or H minus Ts, where H is E plus PV here. So if you write the differential form of G, you basically get negative SdT. So the TdS term has been replaced with SdT, the PDV has been replaced with VdP, and the mu dN term remains. So Gibbs energy dictates equilibrium of your system under isothermal, isobaric and closed conditions. And it turns out that most experiments are actually done under these conditions. So you do them under isothermal, isobaric and for closed systems. So that is why Gibbs energy is a very popular thermodynamic potential that is used in the literature. There is also one other potential that we can define, which is referred to as grand canonical potential. This is the Legendre transform with respect to both your entropy as well as your chemical potential. So you can actually write your d phi as negative SdT and negative nd mu here, the PdV term remains the same. So instead of the mu dn term you have a negative nd mu term here. So grand canonical potential basically dictates the equilibrium of a system under isothermal, isochoric and open conditions. So this is a very relevant potential for a system that can actually exchange chemical species with its surroundings, right. So Legendre transforms are very useful, and these set of differential forms are quite useful to know, because they help us link our statistical mechanics to these specific variables that we have here, such as entropy, pressure, chemical potential and so on. Okay. So continuing on, so just like we defined grand canonical potential, we can also define a semi grand canonical potential. So here you do a selective Legendre transform of your internal energy on the number of species of the system that the system exchanges. So if you have multiple types of species in your system, you only do a Legendre transform of the system that the system is actually open to, that the system is actually exchanging. So this is actually quite useful in terms of both setting up experiments as well as in computational techniques as well. So many let us say ion selective membranes, electrolyte systems and so on, they are all semi grand canonical in nature. So they only exchange one species among all the species that exist in the system. So in order to model those systems, these semi grand canonical potentials are useful, and these are also quite useful in computational techniques to generate your phase diagram. So most phase diagram generations that are done using lattice models and Monte Carlo simulations are based on semi grand canonical potentials. And then the other sort of useful quantities to know are basically specific heats, right. So these specific heats are related to how your thermodynamic potential actually varies with changes in temperature. So basically if you provide some heat input under certain boundary conditions to your system, how does that change your temperature, or the other way around. So if you want a change in temperature, how much heat do you have to exchange with your system under certain boundary conditions. So you can define different specific heats for a system depending on different boundary conditions. So for example Cv is specific heat under constant volume. So this is defined as the change in heat with respect to temperature of your system under constant volume. It is usually defined for a closed system. So you can actually write this as du dt at constant V and N, because so U here is the same as E. So I have interchangeably used U and E for internal energy. So dE is basically TdS minus PdV. So under constant volume, I can write this down here. So your du or dE is basically TdS minus PdV here. So under constant volume this term sort of goes to 0. So you have dE dt under constant volume number of moles is the same as del Q dt under constant volume number of moles equals T ds dt under constant volume number of moles, where del Q sort of comes in because your dE is del Q plus del W, and del W is 0 if your PdV term is 0, right. So that is the basis of this derivation here, right. So just like you have defined your Cv, you can also define your Cp, which is the specific heat under constant pressure, once again defined for a closed system, and this you can define for with respect to the temperature derivative of your enthalpy term here, right. And then one mathematical trick that is often used in statistical mechanics is the Stirling's approximation. So if you have a very large number, right, so the natural logarithm of the factorial of that number, right, you can actually write this as n times ln of n minus n, right. So ln of n factorial for a large n can be written as n ln n minus n, right. So this is a useful approximation to know when you deal with statistical mechanics. Okay, let us now switch gears and talk a little bit about quantum mechanics. So why do we need to understand quantum mechanics? Because this is the theory that sort of largely governs microscopic behavior, right. So if we think about how atoms interact with one another, how electrons interact with atoms or electrons interact with one another, then these are all dictated by your quantum mechanics, right. And if you think about quantum mechanics, the governing equation is the Schrodinger equation, and if we are looking at equilibrium properties, right. So because we want to finally link to macroscopic thermodynamics which deals with equilibrium, right. So whatever theories we develop, we want to link towards equilibrium states of a system, right. So for defining equilibrium states, we have to look at the time independent version of the Schrodinger equation, right. And the time independent version of the Schrodinger equation is fairly simple in terms of the equation form itself. So it is just h psi equals E psi here. H is basically your Hamiltonian which determines all the energetic interactions or contributions. So in a very simple sense, H contains all the potential and kinetic energy terms, right, that your system can have or particles in your system can have, and this is basically an eigenvalue equation, right. So E is basically your eigenvalue, right. So which is what you get when your Hamiltonian operates on your wave function here, and this eigenvalue is nothing but the energy of your system, right. So energy of the system corresponding to this wave function here. So wave function and this wave function can be a many body wave function if you have multiple particles within your given system. So it is a many body wave function that contains all the necessary information about a system, right, about a system, or if it is just a particle, about that particle, right. So the wave function itself does not have a lot of physical meaning, but the sort of physical intuition comes from the fact that the square of the wave function, the magnitude of the square of the wave function is sort of roughly related to the probability that your given system is in some state q, right. So your wave functions are dependent on the state q here. So if you take the value of that wave function, if you take the magnitude of the square of that wave function at the state q here, basically you get the sense of the probability that a system will exist in that state q, and this q can be a collection of variables. So it can be a collection of positions of particles, or it can be collections of momentum of particles and so on. And since probabilities always add to 1, right. So if you think about this net integral of psi square dq, and if you do this over all space, so go from minus infinity to infinity here, it should give rise to 1, right. So which implies that there are well defined, or your psi cannot take arbitrary functional forms here, it should follow this bound, right. So so psi usually should have some well defined functional forms. And your overall time independent Schrodinger equation is an eigenvalue equation, so which implies the analytical solutions only exist for a few problems, for a few situations. More or less we need to rely on some numerical techniques to solve this eigenvalue equation. Okay. One of the most famous problems that you sort of deal with in quantum mechanics once you start studying quantum mechanics is particle in a 1D box, right. So very briefly the problem looks like this, right. So you have two infinite potentials here that basically define a box within which a particle basically exists. So within the box there is no potential, right, there is no electrostatic or electric field potential, magnetic potential, there is no potential term here, and then there are basically infinite barriers, so the particle cannot escape the box, right. So it is trapped within the box, but the particle is free to move, right, within this box, right. So within the box the particle will only have a kinetic energy term because it does not have any potential energy within the box itself, right. So our idea is to find the wave function of that particle and also get a sense of what kind of energy states the particle can have, or what energy values the particle can have within this box. So the Hamiltonian simply only has the kinetic energy term, so this is h bar is basically your Planck's constant divided by 2 pi here. So this is one way of stating your half mb square from classical mechanics, right. So you can use this functional form to represent your kinetic energy. D square by dx square roughly stands for the Laplacian, right, in a one dimensional system, and if you actually go ahead and solve the eigenvalue equation h psi equals E psi, you will see that there is a whole range of possible wave functions that actually satisfy this eigenvalue equation. So you can define one of these wave functions, the nth wave function, basically as the corresponding sine form, right. So for example psi 1 of x would be sine of pi x by a, psi 2 of x would be sine of 2 pi x by a, and so on, right. So there is a whole series of functions that satisfy the overall eigenvalue equation, and the series can be represented as this form here, psi n of x equals root of 2 by a. This is a normalization factor to ensure that probabilities all go to 1, and then you have it's simply a sinusoidal series. So this kind of a sine wave behavior basically ensures that we also obey the boundary conditions. So the wave function should sort of decay to 0 at both your x equal to 0 and x equal to a, which basically implies that the particle cannot escape the box, right. So if you have wave functions of this form, then the corresponding energies, right. So the energies can also have different forms depending on which state the particle is in, right. So if it is in psi 1, then this value would be E1, if it is psi 2 this will be E2 and so on, right. So the energy of the particle in a given state is given by h square by 2m a square times n square, right. So you see that energy is now discretized, it is not a continuous variable, because if you have E1 or epsilon 1 here, it is nothing but h square by 2m a square. If you think about the second energy state epsilon 2, that is h square by 2m a square times 4 here, right. So you cannot have values of 2 h square by 2m a square or 3 h square by 2m a square and so on. So you have discrete values of energies that the given particle can occupy, right, depending on the state that is actually occupying within the system. So we clearly see there is lot of differences between the classical mechanics and quantum mechanics, right. So in classical mechanics we typically do not have any restrictions on what kind of kinetic energies a system can have. So it can usually have a continuous range of kinetic energy values, but in quantum mechanics in a very simple system such as particle in a box, you see that energy is already discretized, right. So there is only a certain finite values of energies that your particle can take, and there are also forbidden values that the particle cannot take. We can now generalize this problem into a 3-dimensional box, right. So we basically generalize this into a cube here, and if you go ahead and solve this, so your Hamiltonian becomes more general here, so it is h square by 2m times your Laplacian here, right, Laplacian in your 3-dimensional coordinates, and then your energy can now depend on 3 different integer values here. So here it only depends on n, here it depends on n along the x direction, n along the y direction and n along the z direction. So you can basically have h square by 8m a square times your nx square plus ny square plus nz square. So these are your energy values. Your nx, ny and nz can have values going from 0 all the way to infinity, but not all of them can be simultaneously 0. So at least because that leads to a very trivial solution, so at least one of them should be a positive number. Yeah, so if you now look at the energy in this particle in a 3D box, right. So this term here nx square plus ny square plus nz square basically looks like a radius number, right. So it is a radius of a sphere in the nx, ny and nz coordinate system, right. So in this sort of quantum number kind of coordinate system, right, in this integer coordinate system, your r basically represents your radius of the sphere, right, corresponding to nx, ny and nz. And these are all positive integers, so this basically corresponds to a quadrant of the sphere that is actually possible, right. So your r square, your r in principle can have negative values as well, right, but since your underlying quantities are all positive, right, they are all greater than or equal to 0, your sphere basically the sphere that is spanned by your energy values here corresponds to one quadrant of this r sphere, right. So the other sort of interesting thing to note is that your energy here, right, can have the same value for multiple combinations of nx, ny and nz, right. So if you have 1 0 0 or 0 1 0 or 0 0 1, right, all of them gives rise to the same overall energy value, right, for your particle in a 3D box, which implies that there are multiple states of your particle which can have the same energy, right, and such states are basically referred to as the degenerate states, right. So the energy states of your system or the states of the system that have the same energy, right, are basically referred to as degenerate states of a system, right, and we can always define the number of degenerate states at a given energy of a system as this variable omega, right. So omega is usually a function of your energy itself, so it usually depends on the energy. The higher the energy, usually the larger the omega is, the more the number of possible states that your system can have at this at a given energy, right. So degeneracy is a very common idea that we encounter in statistical mechanics, right. So degeneracy simply means the total number of states that can have the same energy. We can also define a density of states. So this is basically a number of states within an energy interval, right. So if we think about the overall degeneracy, right, So if you now consider the variation of this this degeneracy over a small energy interval, right, over a d epsilon interval, this is basically your density of states, and usually for a particle in a 3D box this density of states scales as epsilon power half, right. So it sort of grows slowly with epsilon, right. So as you keep increasing your energy, your density of states sort of grows in a square root manner. And because your density of states sort of has this functional form, it is also a fairly dense function for most systems. So in the sense that your quantum mechanics states that your energies are discrete, right. So you have discrete values that are possible for your epsilons, but if you look at your spacing of energies between the different epsilons and in fact put that into this density of states function which is basically omega of epsilon times d epsilon here, you will basically see that this discrete function becomes so dense that it can be considered continuous for all practical purposes. So you will often see in literature people defining a density of states as some kind of a mathematical function and then performing integral operations rather than summation operations within this density of states, and that is largely because it is a very dense function for most systems. So the spacing between the different energy levels or the different densities of states is so short that you can consider that to be a continuous function. Okay. Now let us get to the sort of core idea of statistical mechanics, right, which is the difference between time and state averages. So far we looked at sort of thermodynamics and also quantum mechanics. Now we need to understand or define some kind of governing principles, right, for setting up our statistical mechanics framework. So if you think about macroscopic properties, right, of a given system, you can sort of consider them to be averages of changing microscopic properties, right. So for example, pressure is related to the number of collisions that your particles have against your external surface. Temperature is related to kinetic energy, how rapidly particles can actually move in a given system, and these are sort of more representations for a gaseous system, right. So in general these kinds of macroscopic properties, your pressures and temperatures, are obtained as averages of these microscopic properties over time, right. So you take these averages over a large scales of time. So let us say you do some measurement, right. So let us say you measure temperature, maybe you are taking temperatures every millisecond for example, right. But if you think about atomic movement, atoms actually move at the order of picoseconds, right. So even if you take measurements every millisecond, right, this is actually averaged over 10 power 9 orders of magnitude, right, in terms of time. So you basically get a practically constant value of temperature. So in other words, you cannot get the small variations in temperature that happen in the scale of picoseconds, because you are making measurements in the scale of milliseconds. So you basically get averaged quantities of temperature every millisecond you actually measure it, right. So we can define some kind of we can define this time average, right, basically as so this E of t indicates the average of this quantity E, which can be energy, right, and you can replace this with any quantity here. You can replace this with temperature, pressure and so on. This average is also denoted by E bar, right. So this is a very popular notation in statistical mechanics. So this is average energy, so this is energy, and then bar basically indicates the average of that, right. So the time average energy is basically defined as this integral here. So the variation of energy with time, right, as the time step is taken to be very large quantities, right. So if you take an average of this quantity over very large time scales, that is basically your time averaged quantity here. So that is one way of taking averaged macroscopic averaged quantities of microscopic properties. Another way is to actually average over states. So what I mean by that is, so let us say I have a system, I can now create A copies of the system, right. So this A can be, let us say, a very large number. So just like your time is, let us say you are taking time averages of the order of 10 power 9, I can also create 10 power 9 copies of my system under the same thermodynamic boundary conditions. So whichever is governing my system under those same conditions, I create A copies of the system. So the system is under the same macroscopic constraints, and whenever you have degenerate states, they are all presented an equal number of times. So how many whatever is the value of the degeneracy for a given energy of a system, we take the same number of copies, right. We take all degenerate copies of the system. So this collection of A copies is basically referred to as an ensemble. right. Now what I can actually do is, so once I have collected, once I have created these A copies of the system, I can perform one measurement, right, over each copy of my system, obtain the property of the individual copy, and then I just take the average of all of these copies to get the macroscopic property, right. So in the case of time average, I am basically taking average over time. So here I am taking snapshots, right. So I am taking copies or basically snapshots of a system which are multiple in number. For each snapshot I am basically making one measurement, right, and I am taking an average over all measurements, right. So this is another way to take the averaged quantity of a given property, right. Now how do I actually take the average? Maybe I associate some kind of a probability of occurrence for each copy, and then I weight by that probability, right, because if let us say I take 100 copies of the system and 90 copies turn out to be identical to one another, then that probability will be higher, right. Probability of the system existing in that state will be higher compared to the remaining 10 systems. So I can always adjust this by the probability of occurrence for each copy. And the individual copies of the system or individual snapshots of the system are basically called as microstates. The ensemble is basically referred to as the macrostate, right. So the collection of all the copies is basically referred to as ensemble or macrostate, right. So this is another way of taking averaged quantities, right. Now you have time averages and you can also have these ensemble or state averages. Now which of them is right, right. So that is where this ergodicity postulate comes up in statistical mechanics. So it basically states that the ensemble average of a thermodynamic property, right, is equivalent. So it is basically the same as the time averaged macroscopic value, right, of the property measured for the real system, right. So what this basically states is that it does not matter whether you take the ensemble average or the time average. So the state average or the time average, it should yield the same macroscopic property of a given system as long as the averaging is done over large large numbers. So you take a time average over long time scales and you take the ensemble average over large number of microstates, right. So at the infinite limit, both in terms of your time steps and the number of copies that you actually generate. So as long as these are large numbers, your time averaged value and your ensemble averaged or state averaged value should be the same. And if and this statement basically comes from this ergodicity postulate, right. So mathematically the way we can say is this, the average energy should be the same whether you do a time averaging or whether you do a state averaging, where we basically average it over probabilities of individual states. So I basically corresponds to a given microstate, a given copy of the system. E is the energy of that state in that copy, and P is the probability of that the system will actually occur or exhibit that copy, right. So as long as you know the probability that the system occurs in all states I that are possible within the system, you can basically calculate the average quantities here, right. And it actually turns out that knowing these probabilities is very useful. We will see in the next lecture that once we know the probabilities, we can basically calculate any macroscopic property, right. And just to give a visual example of this ergodic principle, right. So let us say you have a dice and you want to get a count of all the the probability that all the 6 numbers get shown up, right, within a die. So if you throw the die 10 power 6 times, right, so this is a very large number. If you keep throwing the die, right, 10 power 6 times, then you can basically and if you count the number of times it lands on a 1, 2 and 3 and so on, as long as the dice is unbiased, right, it will land the exact same number of times across all the 6 faces, right. So you can take one die and throw it 10 power 6 times, right, or you can take 10 power 6 dice and throw each of them once, right. Both should give you the same statistics. So it is the statistics that we are after, right. So what is the probability that my system will be in 1, system will be in 2, system will be in 3 and so on. Whether you do it you take one die and then throw it 10 power 6 times, which you need to keep throwing for a long period of time. So this is a time average quantity, or whether you take a large number of dice, so you create 10 power 6 copies of the system and then throw them once, right, and then count the statistics, it should be the same, right. So if these two and these two should be the same as long as the number of your time averaging is done over a large time scale and the number of copies that you create in your system is fairly large, right. So, this principle is what is referred to as the ergodicity postulate. This is a sort of interesting problem that all of you can try out, right. So, in a class of let us say n non-interacting or independent students, right, how many students are asleep at any given time, and you are given that the probability of a student falling asleep is basically p sleep, right. So, if you have independent students, so you have n non-interacting students or a sort of n non-interacting particles, they can basically exist in the sleepy state or in the awake state. So, probability that they exist in the sleepy state is p sleep, in the awake state is 1 minus p sleep. So, if you actually do calculate the average number of students who are asleep at any given point of time, whether you do it over time averaging or whether you do it over state averaging, you will get the same answer, right, which is basically the total number of students times the probability that any one of them is asleep, or the probability that any one of them is asleep at any given point of time. So, that is basically the definition of your p sleep here, right. So, it is just n times p sleep. So, whether you do it this way or this way, you should get the same quantity here. Okay, with that we will recap and stop this lecture. So, statistical mechanics can act as a bridge between microscopic interactions and macroscopic thermodynamics. We looked at a brief primer on thermodynamics, right. We also looked at some amount of quantum mechanics, and we looked at the ergodicity postulate, which is the sort of key framework on which all the mathematical framework of statistical mechanics lies on. Right. So, we looked at that, and in the next lecture we will continue our discussion on statistical mechanics, and we will look at a few example ensembles. So, the way you actually create copies of your system. So, with that I thank you all for joining today's lecture. I will see you all in the next one.